Yeah.
Might I trouble you for some tea, sir?
I will share with you.
No, I'm not going to drink out of that. It's chemical equipment. Last lecture in the unit.
Woohoo!
Woo! We're going to use some mole-mole ratios to predict the outcomes of a chemical reaction.
Yeah, mole-to-mole ratios is one of the steps we really need to get right.
They look like fractions, so you're going to freak out.
But don't. And this is something we need to balance our chemical equation first for.
And then we use the balanced equation to do what we're about to show you. So to figure out how much material you need to create or how much material are you using.
So I can make any fraction using any of the coefficients.
Correct.
The only thing I need to make sure is the coefficient I use, I keep that molecule with it. Mm-hmm. That's all the rules.
We're going to show you, it's more dimensional analysis. Letting units be your guide. It's just we're going to use the balanced equation to create the conversion factor and then utilize it.
Right. So here's an example.
Basic mole ratio.
It's balanced, right?
Yep.
2 and 6, 2 and 6. Oh, 2 and 6. Yep, done. It's
balanced chemical reaction.
I can make all sorts of mole-to-mole ratios based on this.
Mm-hmm.
So I could say for every 1 nitrogen, I'm going to make 2 ammonias.
Yep, that's the ratio. That's the conversion factor that he wrote in there.
And where'd I get the 1 from in front of the N2?
He implied it because there's no number written.
In front of the N2. So we use that balanced chemical equation.
One other one you could do is a 3H2 over 2NH3. So meaning like for every 3 hydrogen gas, H2 gases you use, you'll produce 2NH3.
Correct. Mm-hmm. And as long as I'm keeping the 1 with the N2 and the 3 with the H2 and the 2 with the NH3, I can pick any 2 and put them together and it's a ratio.
And you can flip them upside down. You can rearrange them. Like you are making ratios out of the mole coefficients in a equation.
Right. And then here's the last piece of the whole unit, limiting reactants.
Right.
So it is in there.
Yes. Right. It is in there. So limiting reactant is like what you run out of first.
Yeah. So if you're making peanut butter and jelly sandwiches and you go to BJ's, you get the big old tub of the peanut butter and a big old jar of jelly and one little loaf of Wonder Bread.
You're going to run out of Wonder Bread before you run out of the
other.
I
can only make that many sandwiches, and then that reaction stops.
You'll have all the peanut butter and jelly left over, but you will not have any more bread.
Right. So this is a 2-step problem. You got to run the Stoich twice. And run the Stoich means transfer from grams to moles, and then mole-to-mole ratio. Right. And we're done. Okay.
You have to run both reactants to a common product in grams, and the smaller of the answers will reveal the limiting reagent. These are very rare, but we'll try and show you an example. Okay.
Yeah.
We are going to use a mole-to-mole ratio to show the prediction of a synthesis of ammonia. So let's see what equation we got.
I didn't put it.
Oh man, really?
I think so. No. So we're going to actually make it so we go backwards. Earlier we had to write the words from the equation. So Mr. Monaco's got the skills. He can write the equation from the words and balance it himself. So bam, he just did it. And he did it quick. I couldn't even finish saying it.
Boom.
Done.
So that's a balanced equation. It was beginning in the video. We're going to use that.
Synthesize ammonia from my reactants. It's worded funny, but that's actual lingo. But now here's the trick. If I start with 5 moles of hydrogen and 3 moles of nitrogen, which one will be the limiting reactant? So what I need to do is start with 5 moles of hydrogen and run through, and then do it again with the moles of nitrogen and run through.
Which will be the limiting reactant. So,
right. So
check it out. So this is how we do the ratio. So 5 mole.
Start with what you're given.
H2.
And like we did the ratio with the gram formula mass, I want moles of H2 in the denominator of this conversion factor. So for every 3 moles of H2 I put in, that's from the chemical equation, I get 2 moles of NH3. So I do 5 times 2 is 10. 10 divided by 3 is
3.33.
There you go. Moles of NH3. We said earlier that we got to go from grams to grams. Well, guess what? In this case, we can go from moles to moles and be done. We can give you a problem where you have to go from grams.
So now, that was the 5 moles of H2. Now we're going to do for the 3 moles of N2.
Facts. So 3 moles of N2. Now I need moles of N2 as the denominator of my conversion factor. The same way we did the unit or dimensional analysis with gram formula mass. So common product, 2 moles of NH3, but this time it's only going to be 1 mole of N2 because that's what is in my balanced chemical equation. We use the ratio that we just talked about at the beginning of the lecture. So now it's 6 moles of NH3. So what this is really saying is if I start with 5 moles of hydrogen based on this chemical equation, I can make 3 moles of NH3. And if I have 3 moles of N2, I can make 6 moles of NH3. And
But
which one's less?
which one would I run out of first? I would run out of the hydrogen first. So even if there was 3 moles of N2 available, you can't make 6 moles of NH3.
Because I ain't got enough hydrogen to make 6 moles.
Because you didn't have as much hydrogen. Exactly.
So in this case, the hydrogen's the bread. It's the stuff I would run out of. Because once we got to that 3 moles of NH3, there'd still be N2 left to keep going, but we'd be out of the H2, reaction would stop. So circle them up.
I want to clarify one more thing. These conversion factors that I made here,
Yes.
I created
From
From
the recipe.
the ratio.
Notice the 2 goes with the ammonia both times because there's 2 in front of the ammonia in the equation. He chose H2 as the denominator because the first reaction, the first given was H2.
And I was letting my units be my guide.
And what is the coefficient for H2 in the chemical equation? 3.
So that's where I get. So the real number was these 2 and the 3. That 2, that 3 came in here,
Yep. And then we did a
That
2 and a
two.
1.
and that 1 came in here. That's how I created my conversion.
So we just used what we learned at the first part.
You have
of the
another
lecture.
example to do?
I think we have one more.
Okay.
Let's do one more.
Let's
So we
see.
get rid of that. We got to make an equation.
Okay, make an equation and
It
balance
says
it.
decomposition of water into hydrogen and oxygen. So I know I'm going to start with one thing and break it down into 2. And then let's balance. He's going to need a 2 in front of water, I think. And that O is an O2. There you go. Now we good. And then there's our balanced chemical equation.
But let's get the problem.
Here's
If
the
you
problem.
start with 3 moles of H2O, how many moles of H2 and O2 will be made?
All right, so let's start and just go. We got 3 moles of H2O to start with every time. I'm going to need moles of H2 in the denominator of my conversion factor to get rid of it. So that's the 2 moles of H2 from the balanced chemical equation. And let's go into H2 first. So it's 2 to 2.
Okay, hold on a second. 2 mole
H2
H2,
over 2 moles
2 mole
H2O.
H2O.
And I
I
do
got
that
these
specifically so the
from-
moles of the H2.
Here. I got
Correct.
these from those 2.
Yes. So now moles cancels. I have 3 times 2 divided by 2 equals 3. So in that case, I can make 3 moles of H2. Notice H2 is the only moles of H2 is the only unit I have left. I've crossed the other ones out. And we'll do the same thing going into oxygen this time. So the problem says 3 moles of water. Different conversion factor though this time because my coefficient on O2 is different. I have 1 mole of O2 for every 2 moles of water that I use. So that is going to be 3 times 1 divided by 2. 3 divided by 2 is a 1.5 moles of O2.
So the limiting reaction, well, it wouldn't be in a limiting reaction in this
Not this
case.
one.
It's just that if you take 3 moles of H2O, it would be broken down into 3 moles of H2 and 1.5 moles of O2.
And then so when you get a little bit better at this, I could change the problem to say, well, what if I had 4 moles of water? And you'd say, whoa, in the equation, I got 2 moles of water. So to get to 2 to 4, I double, and then you could just double your products. So once you get good at this, you might find that some of them have some easy logical sense, but that's something like this that isn't really a limiting reagent.
You use the mole to mole ratio to double or triple a reaction or cut it in half or figure out how much product is produced when this much reactant is consumed,
Yeah.
to put it in the technical terms.
Yeah. So I'm just gonna make sure we're done. Sweet. And then we can just kind of wrap this up. So the unit is
All about
Complete.
moles and stoichiometry. The hardest part is, personally, I think this mole to mole ratio, wrapping your head around how exactly you set up the conversion factors.
Yeah. I think that if you have trouble balancing equations, that's okay. And my experience has been the unit conversion in the dimensional analysis
grams
piece.
to moles, moles
Grams
to
to
grams.
moles to grams screws people up. So if you guys find out that you maybe need more practice on a particular subject, just come to one of us.
Absolutely.
We'll get you more practice. So
Don't
you can,
sit there quietly grinding your teeth going, oh my gosh, this isn't for me.
no fraction freakouts.
We
We're gonna-
don't think that
practice
these
until
lectures
we-
are the be all end all.
No, you got to get the work done.
You got to get the work done, and that's why you have access to us.
Yeah.
Don't
And we don't
practice till you get it right.
We practice until we can't
Get it wrong. See you next unit.
Click up.
this button and I turn it. Ow!